I hope you're enjoying the course on Python. Um, how are you, first of all? We've learned so much already. We started from data types to variables, all right, to writing some decision-making logic using if-else, to for loops for iterating something. And then we learned so many data structures wherein list and tuples can be very powerful if you want to create a sequence of elements. Dictionary can be so much powerful when you want to extract data using a particular key. And sets are your friend in case if you want to combine a lot of things or see an intersection, all right, and anything like that. Now today, it's a very interesting class, okay. In fact, this module is very interesting, okay, because this is where the real things happen, all right. Until now, think like, you were making uh, a UAV project, okay, just making an MVP, all right, which can just perhaps, take a fleet of some 30 meters, etc., etc. And now you are actually building a real autonomous flying vehicle, right? So it's like that. Why do I say this, right? It's because of three very powerful libraries that we will learn in this module. We'll start off with Numpy, which is essentially what this specific lecture is about. All right. We will then delve into pandas, and then we will learn two libraries. One is Matplotlib, the other one is Savan. Okay. And these have a very different role in how AI, machine learning, data science has shaped today's world. Think of anything in data science, think of anything in AI, all right? Everything is powered by at least one of these libraries, okay? Or perhaps their inheritance, okay? Uh, I would just say that mastering this particular topic would be very helpful, okay, in order to do anything in data science, machine learning, LLMs, learning transformers, building AI agents, etc., etc. So focus on this module and learn it. Give your heart and soul towards understanding it. Uh, Today we will start with Numpy. Okay, uh, it's very interesting because some people call it Numpy. Okay, some people call it Pi. Okay, and perhaps you can tell us in the comments which one you are. Okay. I am a NumPy person for all the right reasons. But yes, do let us know. It doesn't matter actually whether you call it NumPy and NumPy, but what matters is how powerful it is. And let me tell you a story uh, to explain the very importance of NumPy. NumPy actually helped me pass a course in machine learning. Okay. It's like if I have to make noodles, Hakka noodles, okay, first I would have to boil the noodles. I would have to chop some vegetables, put in some masalas, etc., all of that, put in some oil. That essentially what I was doing in my machine learning project. All right, writing a lot of for loops, okay, nested for loops, everything. And think about NumPy as this 2 minutes uh, instant noodle solution, wherein you just stir something and it's done. All right. So whatever you've done until now, you would see how you can just do it with NumPy much more easily. And not just that, you would see how NumPy and libraries like NumPy are actually powering today's transformers, models like ChatGPT and neural networks. So let's get started. Uh, for this module, we will focus on something what is called as a Jupyter notebook. Jupyter notebook is nothing but it's essentially a sequence of code cells. So until now, what you had is just one code cell wherein you type something, couple of statements, run it, and it runs all the statements. And it was difficult, right? We've seen, right, that I would have to comment out all the past statements in order so that it doesn't run it again. Now imagine that I have these separate blocks which I can run, which I can execute separately. Okay, that's what Jupyter Notebook is. And cherry on cake, you can actually convert it into a proper notebook by adding headings, by adding paragraphs. You can even add images, you can even embed videos. So the most interesting Jupyter notebooks are actually what they're called as. They're actually notebooks. Okay. Uh, I'm going to tell you how you can access one, although you can have a Jupyter notebook set up in your laptops, in your personal computer, in your local as well. But I would suggest that you start with a Google product. Why? It's online, it's cloud based, and everything is just much more easier. Okay. So you go to your Google, your favorite search engine, and I don't know if your search engine is a Google search anymore, or perhaps something like Perplexity, or you're just using ChatGPT as your Google search. But I will stick to it. I will just say Google Colab. Okay. It says welcome to Colab. Okay. It's a Google product, as you can see. And as soon as I click, it actually opens up a new notebook for me. Oh no, it shows me if I want to open some other notebooks that I've worked with, or I want to create a new notebook. Okay. So I'll just create a new notebook for you. Okay. You can perhaps, pause this video here and do along with me. Okay. And come back when you're done. So here, this is essentially what it starts with. Okay. And it's very simple. If you want to just write a code, let me say x equals to 2, print 2. Okay. I can just click this button, as you can see, which looks like a play button. Okay. Just put this up, run this, and it will take a little time to kind of like connect to a Google server, okay, for executing. But then once it is connected, okay, it will be pretty fast. As you can see, it gives me an output. Now I can add a text cell here, say, okay, this will be my first text cell. And then what you can also do, instead of playing, you can enter shift and enter. You can press shift and enter together. That actually also does the job of running a particular cell. Either it's a code cell or a text cell, whatever. Now, if I write something over here, okay, let me say again X, okay, what you will see is that whatever I have run in the memory, okay, it stays in the memory. So this is my current runtime environment. Okay, I can stop my runtime environment by saying disconnect and delete runtime. But if I have ran something, okay, and I am still in that runtime, it will store all the variables, it will store all the objects that I have created. To give an interesting example, if I want to, let's say, add another cell over here, let me just say maybe x plus 2, okay, x plus 1. Okay. Now it does x plus 1 for me. Okay. Why? Because x was already present, right? Even if it's above this one, even if I take this up, okay, as the very first statement, even if I run this right now, it will actually run for me. Okay. I can just maybe make changes and show it to you that, it will work. However, if I have disconnected from here, and if I have let's say, restart the session, okay, now if I try doing x plus 4, okay, it will give me an error. Why? Because it could not find where x was defined. So I will have to define it again. I will say x equals to something, let me say 0, and yes, now it will function fine. Okay. As you keep on using Jupyter Notebook, you will get a better hang of it. You can just simply use this play button or press shift enter. Okay. Shift and enter to kind of run a cell quickly. And the entire next module, which will be focusing on NumPy, Pandas, Matplotlib, Seaborn, these Python data science libraries, or I would say Python AI ML data science libraries, we will be using a Google Colab. Okay. Now, in order to save some time, what I've done here is I have pre-created a Colab notebook, right? I added some headings over here. I added some subheadings. I added some code, which I wouldn't have to write again, so that we can go faster. Okay. Let me maybe write this content at least. Okay. Or I may have another notebook which doesn't have this much of wordy content. Let's stick to that. Okay. Cool. Now, the first thing that I will do here is I will say import numpy as np. Okay. I am saying that, hey boss, import numpy and call it np. I can literally call it anything. I can call it Rahul, I can call it Vishal, I can call it my name, I can even call it anything, literally any variable name that you want to give. All right, you can give technically to this, right? But np remains a standard alias. And what do I mean by alias is, alias is anything but like, a standard short notation of anything. So a very standard short notation for numpy is actually np. Okay, so I said import numpy as np, so that if I want to use this numpy module, I would call it as np and not numpy or anything else, right? You can call it anything if you'd like, right? Now, what I've done here is I have created a list. You're aware of list, a sequence of elements. Here it is a sequence of integers, and it's fine. And I've saved it in a variable called a, right? Now, if let's say, if you have to do this task, okay, of adding an element to each element, how would you do it? Very interestingly, you would see that, uh, since Google Colab is powered by Gemini, okay, it will actually, explain the code for you, sometimes gives you some autocomplete suggestions, etc., etc. See, it is actually giving me a autocomplete suggestion of how you can perhaps use it. And I press a tab, and this actually writes code for me, okay? I made Gemini write this code for me because, we have learned it before, all right? So what it is doing here is it's saying for I in range in length of a, which essentially is saying that, you run this for loop n times, or basically equal to the length of the list. And what you do is at every element, you increase that element by adding +2 to it, right? We could have done it in a much more easier fashion also. I could say I +2 for I in, let me not call it I, otherwise we'll get confused. Let me just call it A, okay, or something. Let's say B, for B in, let's say A, okay. So I'm saying for every element, okay, let me just call it element, okay, for every element in A, okay, add +2 to that element and store it maybe in A again. The only difference here is that this is a list comprehension. This will create a new list, right? The earlier code actually updated the list, right? So we do not want this. We want to keep the old list intact, right? So we will stick to this. Okay. Now I'm going to show you how you can do this in NumPy. I will say np.array, and within this, you can just provide the list that you want to create as a NumPy array. Okay. We don't call it a NumPy list. We call it a NumPy array. And in about 10-15 minutes from now, I will explain why we call it NumPy array and not NumPy list. But let's just stick with this thing, right? This is a list that I want to convert into a NumPy array. Okay. I could instead say A also here, right? But A is changed, right? So let's not call A, but let's stick to writing it like this, okay? And I will call this as AARR. ARR stands for array. So I'm just saying that, hey, this was a list and maybe this is an array, okay? Now, just guess how easy will it be to write something like this in NumPy, okay? I'm going to show you. I'll say print A RR, which is the name of my array, and I'll just simply say +2, okay? And this does the job. This is the very fun part of it. What I'm doing here is that I am telling NumPy, hey, I want to do this operation with all your elements. Whatever you are saving, just do this operation on this. If I say multiply by 2, okay, it will multiply 2 with every element present in that NumPy array. So imagine for loops are gone. You don't have to iterate anymore. You can just say that hey is an array. Okay, here are so many elements. You just do whatever operation that I want you to do on every element present inside you. Okay, so for loops are gone technically. You'll be thinking कि for loop सीखा ही क्यों भाई? For loop की जरूरत पड़ेगी, ठीक है? बहुत सारी चीजें हैं जो NumPy array से नहीं कर सकते. However, However, NumPy arrays are super, 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 super strong. Okay. So we can see that one of the edge that we have, okay, for using NumPy is to actually have a cleaner code. Okay. And um, we'll see how we can make this code efficient. Let me just charge my laptop and get back to this thing again. Okay, so until now we have seen how you can write cleaner code with NumPy, right? Let's say if you have to perform any operation on all the elements of any list, right? You would choose to actually use NumPy array. Why? Because you can just assume that that NumPy array is nothing but an element in itself. All right, it's an element, and you're just performing that operation on that element, right? Uh, but that's not all. NumPy allows you to actually uh, write much more efficient code. Okay, so we'll see a couple of examples. The only thing that I'm changing here is that instead of this list which has some 7 or 8 elements, I am creating a list of 1 lakh elements. All right, if let's say if I have to do some operation, for example, let's say adding 2, which is what you've been doing until now, I'll just do it. So I'll say for element in, let's say, a list. Okay, what do I want to do? I want to do element plus 2, correct? Now, to do this operation, what we will do is we will check how much time at an average, okay, a Python native list will take. All right, in order to do that, if I kind of want to check the time duration at an average to perform an operation, all right, taken by a particular statement, all right, in Python, especially in Jupyter Notebook, I can use a percentage time it. Okay, let me just run it and show to you. Now, what this will do is it will tell me at an average how much time this operation will take. Okay, so this is telling me that, okay, boss, it will take me about 5 milliseconds, okay, to do this operation. Now, let me actually do the same operation for a NumPy array. Okay, how will we do that? I'll write again time it. Okay, I'm saying just time whatever I'm doing, and Gemini in Colab Notebook is smart enough to suggest me that hey, you write this. Okay, let me run this very quickly, and the answer comes to be 55 microseconds. Now, to give it an idea about microsecond and millisecond, right? 1,000 microseconds make a millisecond. Okay, so it's 51 operation like such. Okay, took 55 microsecond. That means if you do about 15, 16 more operations, that is how much time. Okay, even this operation for 1/5 of the list will take. Okay, if you didn't get the maths, simply a microsecond is much smaller than a millisecond, right? And this code is actually 100 times faster when you write in NumPy, right? So not just you have clean code, you're getting an efficient code also. Now, to motivate a little bit on using the usage of NumPy array, okay, what I've done here is I've defined two 2D NumPy arrays, right? By now, I'm hoping that you know of what a list is, what a 2D list is. 2D list is nothing but what? It is a list of lists, right? So essentially every element in this 2D list, right, is a list itself, right? So this element is a list, then the other element is list, right? And since I've wrapped it up in np.array, it becomes a 2D NumPy array. Similarly, L2 is also a 2D NumPy array. I can perform any operations on it. I can just say L1 plus L2. Let's see what it does. It actually gives me a sum of these two arrays element wise, right? So let's say if I sum 1 and 7, okay, this will give me 8, right? I could do L1 into L2 also, right? And I can technically do any element wise operation. I can compare, I can multiply, I can divide, etc., and so forth, right? But the most important task wherein NumPy proves to be a game changer is matrix multiplication. Why? The neural networks, AI, most of the AI stuff that you're building today, all right, is on top of neural networks, right? Transformers are neural networks. LLMs, Chat GPT, all of this is neural networks. And do you know what is the core of neural networks? It is matrix multiplication. It's the matrix multiplication operation that we study in class 11th and 12th. Okay. Most of the boards have it. I am assuming that, you may have done some bit of matrix multiplication. If you've not, it's a very, very simple operation. Okay. Now, I will just show you a one quick example of multiplying a matrix of size 2 by 3 and a vector. Vector is of size 3 by 1. Anything which has only one dimensional would be a vector. Okay. I will just show you how easy it is to write this in NumPy. Let me say matrix, okay, at the rate. Okay. Why at the rate? Because if I put multiplication sign, it will do an element wise operation, just like what we saw here, right? We don't want to do this. We want to do matrix multiplication. So I'm going to write at the rate here. That's basically a short form for performing matrix multiplication. All right. Now, let me just take this time to kind of summarize what we have learned in NumPy so far. NumPy helps us write the cleaner code, right? It helps us write the cleaner code. How? You can just assume that this big NumPy matrix or NumPy array, whatever, right? Whether it's one dimensional, two dimensional, three dimensional, etc., and so forth, you can just think of it as one single element. And how would you do that operation on one single element? You can do plus, minus, multiply, etc., on that element. And just assume that NumPy will take care of doing that operation for all the elements present inside a NumPy array. Now, this specific thing, although very simple, people often use a very hectic word to kind of explain it. This is called as vectorization, all right? Just very wordy, I know you wouldn't like it, but yes, people just, when they say vectorize, it essentially means that, you don't use any for loops. You just treat the entire array as an element and perform some operation on that, all right? That's what it literally vectorizes, right? NumPy not only does that, NumPy helps us writing an efficient code. You could see the same operation that I would do by iterating on each and every element one by one in NumPy, in a Python list, right? You can do much more efficiently in NumPy. Okay. And the most important one, LLMs, neural networks. At the base level, they are just matrix, and NumPy allows us to write very efficient and very clean code for this. So you can imagine, if at all in your daily life you're using any kind of AI, any kind of machine learning model, neural networks, Chat GPT, etc., it is nothing but lot of matrix multiplication operation. Do check it out. Just Google search, you would find a lot of stuff, right? And you'd be surprised that it is just doing matrix multiplication again and again and again and again and again. So forth. Now, we have finished the first part of NumPy, which was essentially understanding why this library is so important. Now, let's start getting into the nitty-gritties, just so that you can do these operations, understand these operations better, and utilize it when you start learning data science and machine learning. Okay. So the first thing I will do is I will explain a couple of operations, okay, of creating a NumPy array. Okay. I think the first one is something we have already used, so we don't need to understand. You put something inside as a parameter to this function and just call np.array. That would essentially convert any list or anything essentially into a NumPy array, right? A NumPy array. Now, depending on your use case, you can have a one-dimensional NumPy array, which is nothing but just simply like a list. You could have a 2D, you could have a 3D, you could have 4D, etc., and so forth. And you can reach up to n-dimensional array. Imagine the world is built in 3 dimension. Okay, people say that time is my 4th dimension. With NumPy, I can actually work in an n-dimensional regime. Okay, imagine how amazing it is. All right. The next thing is that if, let's say, if you have to create a NumPy array with a sequence with certain steps, what do? You use a range function, right? You do, right? Let's say range. Let's start from 1. go up till 100, and let's take a step of maybe, I don't know what, 10, right? That will create what elements? 1 followed by 11, followed by 21, then 31, and so on and so forth, up until 100, right? Whatever is excluding 100, correct? Instead of range, in NumPy, you call it np dot range. No, np dot arange. All right, arange, right? And I'll just tell you just in a bit why, it is different from a typical function like range. What else NumPy can do, which a typical Python range function cannot do. Okay. But yes, we will see some other interesting use cases like Linspace. And then, you can create an array of zeros, you can create array of ones, you can create an identity array, and so on and so forth. We will be getting into this, seeing this on a playground in a Jupyter notebook one by one. All right. So let's do it. So I'll start with creating a NumPy array. I am not doing this because we've done it 2-3 times already, but just for you to understand it clearly, how I define a NumPy array, I can define it like this, right? And I can pass any tuple, any list, or anything that would convert into a NumPy array. Now, here, if I have to create a sequence, as I said, in native Python, I would use a range function, right? In NumPy, I will say sequence array equals to np dot arange, okay? And I'll say 1, 100, 10. Let me just quickly maybe print this sequence, okay? Let me run it for you. It created the sequence, right? Now, interestingly, if I would have to convert this and say take a step of 10.5, I'm saying that, hey, I want to go from 1 to 100, but instead I want to take a step size of 10.5. Let's try doing that. It works, right? 1, 11.5, 22, 32.5, and so on and so forth, right? Let's try doing this in regular Python. Let me say range, okay, 1 to 100 and 10.5. Let's just see what happens. It gives me an error. It says float object cannot be interpreted as an integer. That means in a range function, all the 3 inputs that you provide, which is the start, the end, and the step, all of them have to be what? Integer. Whereas NumPy actually gives you a power to actually have them float as well. So technically, it is much more powerful. And for a powerful thing, we would not call it the same thing. We wouldn't call it np.range. We call it np.arange. A is what? Array. All right. So we have learned how to create NumPy arrays. We have learned how NumPy arrays are super strong and faster. Let's dive into creating and working with some n-dimensional arrays, right? Until now, we just worked with one-dimensional arrays. I'm going to explain and take 1, 2, or 3 more use cases of 1 or 2 dimensional, and then we'll start getting into 3-dimensional space, 4-dimensional space, and I'll start generalizing things, okay? All right, so let's actually start working with n-dimensional arrays. We'll start again with 1D or 2D so that, it's easier for us to kind of incrementally build on, okay? So here is array 1, okay, which is 1D, and array 2 is 2D, right? The first thing that I want to do is, I want to actually just find the number of elements of my 1D array, right? You can simply use what? Len function, okay? You can simply use len and say arr1, okay? Let's see what you get. You'll get that there are 6 elements. Now, I'm going to actually introduce you to one more function. You say arr1 dot shape. Let's see what this shape gives. Now, shape is actually giving this to me the same thing, but it is giving me in a tuple. We'll just get to understand why it is different from this. So hold on for a little bit, just for 1 minute, okay? You'll just be able to understand why is it doing so, okay? Now, I will do the same operation for a 2D array. I will say, okay, tell me the length of this array, okay? This is going to tell me that the length of this second arr2 is actually 2. Now, take a pause here. Just pause your video. Maybe think for 10 seconds why it did give me 2, why it did not give me 6, why it did not give me 3, why it did give me 2. Because the length of the outer array is actually 2. There are 2 elements in the outer array. Can you see? The first element is this one. The second element is this one. There are just 2 elements in the outer loop, and that's what essentially length gives. However, if I say print arr2 dot shape, this will tell me what exactly is the shape. Now this is saying that on the first dimension, okay, and hear my words clearly because this will be very helpful for us to understand the later concepts, and there's a reason why I'm speaking like this. In the first dimension, I have 2 elements, okay, and as in I go in my second dimension, which is this inside list, there are 3 elements, okay. A better way to think about it is as follows. If I think of this 2D array is like this, okay, your first dimension is this one, okay, the vertical one. Your second dimension is the horizontal one. Let me just mark it for you. This is my first dimension. This is my second dimension. Can you see that there are 2 elements along the first dimension and there are 3 elements along the second dimension, I'm sorry, right? And that's what essentially this shape thing is telling me, that hey, it is a 2 by 3 matrix, or it is saying that I have 2 elements along my first dimension, and I have 3 elements along my second dimension, right? Now you can guess why this was written in bracket, because it is saying that, I just have 1 dimension, okay, and it's 6, and then other dimensions are undefined, okay. Did you get this idea? Maybe just try to absorb, assimilate what we have understood, okay, what we've learned. Just spend 1 more minute, okay. We can do a couple of more interesting examples so that you understand it better, right? But let me just explain the concept of dimensions by taking this specific example, okay. I had what? Let me just check. 1, 2, 3, 4, 5, and 6. So this is my first list. This is my second list, okay, and this is wrapped in another list, right? Now think about it, okay. Earlier, when we just had one list, let's say 1, 2, 3, this is the only dimension I have, and I'm going along this, and I have 3 elements here. Now when I added one more list over here and created a 2D list, okay, so one more element got added here, and now along this side I have 2 elements, and I'll call it as a 2 by 3 2D array, right? So the new access always come from the left side, correct? The new access essentially would come on the left side. We'll see more examples. Let's just try to understand. This is a scalar, okay, it has no dimension, okay. This is a number, okay, it has no dimension. When it turned into a vector, basically it got 1 dimension, which has what? 3 elements. So I'll write it as 3 comma, okay. When we started moving in 2 directions, okay, so we saw that along the first dimension I have 3 elements, along the second dimension I also have 3 elements, so this becomes 3 comma 3. Now this is the most interesting one, okay. Along the first dimension I have 3 elements, along the second dimension I also have 3 elements, and this is my third dimension. Think about it. Am I thinking about it right or wrong? Is it my third dimension or my first dimension? Your first dimension always, your last dimension will always getting added from the left side, okay. So when you had a vector, you basically added one more dimension to it in the left, and it became 3 by 3. Now you're adding one more dimension, which is essentially taking a stack of multiple 2D arrays right on top of it. You can think of it as like a cuboid or any 3D object, right? the dimension is getting added in the left side, right? So this will become 3, comma 3, comma 3, right? If there are 3, no, there are 1, 2, 3, 4. There are 4. So this will become 4, right? I hope you are able to understand the idea of dimension. So you can think about this, right? If you're standing here in a particular direction, you don't have any direction. You're directionless, all right? Essentially, if you are at scalar, you're dimensionless, okay? When you actually go in a particular direction, all right? When you start navigating, all right, you start going in a particular direction, right? That's what makes you 1D, right? Now, when you kind of start building up such things, right? You think of stacking, such lines on top of each other, right? You build a plane, right? Now think of stacking these planes, all right, on top of each other. That will actually give you a depth also, and that will become a 3D object. Now think of placing these 3D objects in a particular dimension which we can't visualize because we are humans and we can think of a 3D space only. But you can imagine placing these multiple boxes across different time points. Think of a YouTube video, okay? You have one frame, all right? And it goes, something changes in every dimension, right? I mean, something changes in every second. That's the time direction, right? So you can think of an object actually moving, all right, a long time, right? So that is essentially the fourth dimension. And now try thinking about n dimensions. You won't be able to, of course, because sadly we're stuck as humans in a three-dimensional space, right? But you get an idea, right? What I'm saying. You'd be very excited to know that an image is actually a 3D object. It has 3 channels, okay? So an image has 3 channels. One is R, second is G, and third is B, okay? RGB. These are primary colors that you can see, all right? So any pixel that you see at any point, right? So any one pixel, okay, which is like, one little point on the screen that you see is mixed of 3 colors, R, G, and B in certain proportion. That's, you can actually create any color using, just three numbers essentially, right? That's RGB. So this is actually a 3D object. If you'll see, these are 3 2D list placed together. And now if I travel in one more dimension, which is time, this becomes what? A video. So an image turns into a video. So video is actually a 4-dimensional object, right? And when we see a video, we see it in 2D, of course, but then in the very core of it, in the very crux of how video is stored in forms of numbers, all right, is actually a 4-dimensional object, all right? I hope you are enjoying this. Let's try maybe indexing and slicing these arrays, okay? So I'm going to start with a simple array 1, which was a 1D array, okay? I am going to say, give me the 4th element, okay, of this array. How will you get the 4th element? You can start actually coding along with me, because this is something simple. You have done indexing, slicing a couple of times. By now, you should be able to attempt these alongside me. Just pause, attempt, then start, then pause, attempt. All right. ARR1, okay. And then I will say the 4th element. What will be the 4th element? This is 0, this is 1, this is 2, this is 3, and this is 4, right? But we want to get the 4th element. That means we should be using what? Index 3, right? So I'll say ARR1 index 3, and this gives me the 4th element. Okay, some indentation error. Okay, so forgot to indent it properly. But yes, this gives me what? My 4th element. 4th element is what? 67, and it's showing that, it's an integer 64 numpy object. Okay, let's try to slice from index 2 to 4, but I want 4 to be inclusive. Now, if I want 4 to be inclusive, shouldn't I say array 1 start from index 2 and have 4 inclusive? So I would have to write what? 5, right? Let's just quickly run. Okay. Now the interesting part is when 2D arrays comes into the picture. Okay. Just for your ease, I will try to write the 2D array like this. Now it is saying access the second array, index 1. Now, which one is the second array? Sorry, second row. Second row is this one, okay? And I have to access index 1. That means I want to index 5, right? Do think about it. How can I do it? I will say array 2, okay? And in this one, I will say, hey, access the second array, right? Second row. So I will say 1 and then I will say again 1, right? This will give me essentially what? 5. But here is one interesting thing. This is how you do not write in NumPy, right? Because what it will do is it will first slice off this part and then slice off this part. However, this is not computationally efficient, right? If instead you end up writing like this, right? All the dimensions separated by comma, right? You would be able to, NumPy would be internally able to slice this as one single go, one single attempt, right? So that's how you write NumPy code. It's okay to actually slice in steps. You slice across the first dimension, then you slice across the second dimension, then you slice across the third dimension. But this is how you should be ideally doing it. Let's give it a try for one more. It says access second of the first row. So you want to access the second element of the first row. First row is this one and second element is this one. How will I do? I will say array, okay, first row, that means 0, comma, I want to access the second element, right? So I will use index 1 over here, okay, and that's how, oops. That's how I will access it. Oh, I should be saying array 2. Perfect. I hope this is clear. Let's try one more, just one more for indexing and slicing, and we'll try to kind of update, do some changes in the array just after this. But the last one says, hey, I want to access the second and third elements of the first row. Okay. So this is the first row and I want to access the second and third element, which is what I want to access. I want to slice 2 and 3. What will you say? Hey, across the first dimension, I want to access the first element, which will be at index 0. Okay. And then I want to access these elements, right? That means starting from positional index 1 and until the end, right? That's how I can write it. And this, okay, again, it should be array 2. It gives me 2 by 3, 2 comma 3, right? I hope that you're able to understand because you've learned indexing and slicing before also, okay? If you are not able to understand this, I would generally suggest that you go back and check indexing and slicing basic tutorials. You do a couple of questions before you come back, right? But ideally, this part should be quite graspable, all right? In the next part, we will check, how can we make certain updates, okay, to a NumPy array, okay? So let's switch, do some questions, and we start learning more. Okay, so until now, we have learned how to work with 1D array, 2D array, and in fact, we've learned 3D array also. We learned how you can index them and slice them. Now let's see how we can update any elements at a particular array, right? So let's say if this is my array, okay, this is my array 1. I'm just going to copy paste this, okay? So if this is the array I'm working with, I want to replace my element at second position, which is essentially at index 1, okay, with some value, okay. I will write this and I will say, okay, change it to 12 maybe. Let's say change it to 12, okay, and I'll try to print the array. This actually prints me the answer, okay. But let's try to do something interesting. Let me try to update it with some character or some string, okay. So let me just say maybe okay. Let me try doing this. This is giving me an array error. Now why? It says that it's an invalid literal for integer with base 10. Now what is happening in NumPy here is that NumPy can store, although any kind of data type. It can store integer, it can store float, it can store string, it can store boolean, but you can only store one kind of data. And that's the only one part where NumPy array is actually inferior to Python list. But here, was an intentional decision taken, okay, in order to optimize for the efficiency, right? So the flexibility that you lose, that your lists are versatile, you can store any kind of elements, okay. For a NumPy array, all the elements have to be of the same type, right? And it allows NumPy to actually store them together in a contiguous memory fashion. All right, you don't need to get into all the details about all of that. I'm just saying it for the sake of it, for the sake of completion. But this is essentially what actually powers NumPy to do all the calculations, everything much more faster. And turns out the reality is that most of the operations that you'll do in mathematics, right, will just have one type of uh, 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 operands, right? It will have either integer, it will have either decimals, it will have strings or whatever. And neural networks, it's all floating numbers, right? It's all decimal numbers. So it works, right? So something like this won't be possible. However, if you happen to define a NumPy array with strings, right, then it should be okay, right? But the type of the NumPy array, okay, has to be different, okay? And when you define a NumPy array, it automatically detects, what type it is, right? So in couple of answers you might have seen when we tried slicing a particular value, it says that it's of type integer. Okay, cool. Now let's try maybe some operations on NumPy array. All right, just because it's simple, so I'm not gonna write it, okay, to save some time. But if let's say if you have a list, okay, you convert it to a NumPy array. If you want to calculate this mean, you can just say np.mean. Okay, you want to calculate its median, you just say np.median. You want to calculate the max value, you do np.max. You do np.min. You can do np.sum. You can do np.prod. And whatever typical, very popular or very common operations that you have to do, turns out NumPy will actually have a function for it. You can just Google NumPy function, how to do this, and NumPy, etc., whatever you want to do. And NumPy most likely will have a function defined for it already, so that you do not define a not so efficient code. All right, they figured out for us what's the best way, what's the nicest way to do it. We will see its power when we work with 2D arrays or 3D arrays. All these functions that we are working with, np.mean, np.median, np.max, all of this will actually be applicable on a 2D array, 3D array, 4D array, and so on and so forth. Okay. Now, here comes the next thing. Okay, we start working with a multidimensional array. I'm just going to leave all of this. You can just perhaps try it on your own. np.prod, np. Here I'm just checking the size of the NumPy array, all of that. All of this is very much easy. Okay, I think one thing which I can stress on is this function. So let's say if you have this NumPy array, if you do np.unique, okay, and say salaries 2, okay, it will actually tell you how many unique elements are there. Sorry, how many, which elements are unique present, which of the unique elements are present here. So 10 is there, 15 is there, 20 is there, 25 is there, 30 is there. Then 15 and 20 is repeated. So it's in a way is actually giving you like a set, right? Remember a data structure called set, right? In Python, right? That essentially it gives you all the unique values. If you want to find number of unique values, you can just say np.nunique. Okay, number of unique, right? So this will give you. Oops, there's no. Okay, that's perhaps pandas. It should be n unique. Let me just quickly check. See, this is the beauty of learning how to code. You don't have to remember all the functions, and that's why I chose to actually not remind you or teach you one function. You can just Google. All right. Turns out np.nunique doesn't work. What works, I can check. I can say unique values in NumPy count. Okay. Let's see if there is a function for that. It says numpy.unique, which is something I know. And it says, oh, you can say return count equal to true. So it will start giving you a return count as well. Okay. So let me just try it. I will say return counts equals to true. Okay. See, you do not have, as a Python engineer, you do not have to remember the functions. All right. You should be able to figure out how and what to use to get the best thing from your part. Okay, and that's pretty much sufficient. Okay, so if in case if you just want to find uh unique values in this list, you can just say np.unique and you're done. It tells you how many unique values are present. Okay, uh go back, check a couple of functions. Okay, np.mean, np.sum, try it out for a couple of values, check that your answer is good, and if you are able to understand it, we can move forward. Okay. Okay, so now it's the good time. We start working with n dimensional and 4 dimensional, 5 dimensional, etc. is like super fun. Okay, so here if you see, what I have done is I have actually created two two-dimensional arrays. Okay, two-dimensional arrays. When you stack two-dimensional arrays, essentially that gives you a 3-dimensional array wherein you will have two elements in the outermost list or array. What it means is as follows. Let me go to the slides to explain a little more. Okay, so this is my first array. Okay, this is my second array, and this is 2D, this is 2D. When you stack these together, a new axis of two elements, okay, is created, and the dimension of this will be 2, comma, this is what, 2, and this, which is what, 3. So this array essentially will be a 2 by 2 by 3 array. Try to look at it a little more clearly. So you'll see that a 2D array that you created over here is actually a 2 by 3 array, a 2 by 3 array, right? Or a 2 comma 3 array. When you try stacking two of them together, you add one more axis towards the left side and it becomes 2 comma 2 comma 3 array. Okay, that's what essentially a 3D array is. Let's try to understand if we understood this concept properly or not. So for that, let me just perhaps show a couple of examples. So first of all, if I create such array and if I try to check the shape of this will give me 2 by 2 comma 3, 2 comma 2 comma 3, right? I can also check maybe length of T1. Okay, when I check length of T1, what do you expect? What will be the answer? Give it a pause, give it a try. The answer will be 2. Why? Because in the outermost list, there are only 2 elements. There is one more interesting function, attribute that you can check. That is T1 dot size. What is your guess? There is this length, there is size, there is shape, so many things. What is your guess what size will do? Size essentially will actually tell you the number of elements in the array in total. Doesn't matter what's the axis, how many axes, how many dimension does it have. It just plainly tells you how many elements together are there in this array, right? And as you can see, there are 6 elements here, 6 elements here, and that's why 12 elements in total. Should we try perhaps maybe trying a couple of examples on this? Should we try that? Okay, so the first thing is that I may want to know, oops, let me just remove these parts so that we can perhaps try it by ourselves. The first thing that we may want to try is accessing the first 2D block. Okay, I am saying that I want to access the first 2D block. First 2D block essentially is this, right? How can I access this? This is the first element in my first dimension. So can I say T1, okay, provide me the first element in the first dimension? That gives me the first block. Okay. Second question says accessing the second row of the first 2D block. Now I still want to work with the first 2D block, which is this one, but I want to access the second row. I just want to access the second row. Okay. So on top of this, can I say T1, okay, I'm going to access the second row. Okay. So 0 for accessing the first 2D array and then 1 for accessing the second row, right? But hey, we learned that we can do a better job by actually writing it like this. And this actually allows me to access the second row in my first 2-dimensional array. Okay. Hope you are able to understand. Just rewatch it. If you're not, you'd be able to understand. Okay. Accessing the second element of the second row in the first 2D block. We're still in the first 2D block. Now I want to access the second element, which essentially will be the uh, second row. Okay. And what would I want to do? I want to access the first 2D block, and within that I want to access second row, and within that I want to access the second element. Okay. So it's simple. I mean, you can think about it. Second. No, first, second, right? So T1, 0, okay, 1, comma 1, right? That gives you 5. 5 is where? 5 is here. It says access the first 2D array, okay, first 2D array, and within that access the second row, okay, and in the second row give me 1, as in the element present at index 1, which is what? 5, right? So you get 5 from this. All right. Let's maybe try doing a couple of more operations on this. So if this is the 2D array, let's say if I have to take mean of this, I will say TP T1 dot mean, and this will give me a mean, right? This will give me a mean. But here is the interesting part. If I say, let me add print to this. If I say print T1 dot mean, but I am asking this to give me a mean in a particular direction. Okay. I say that, hey, give me the mean across axis 0. Now, axis 0 is this one. Let's see what happens. Okay. I'm going to say axis equals to 0. Okay. So the answer we get is 4, 5, 6, 7, 8, 9. Let's try to understand why it is coming. Okay. This is the most important bit. Okay. You have to figure out why taking a mean of this along axis 0, okay, is giving me 4, 5, 6, 7, 8, 9. Okay. If you have to understand this concept in an easier fashion, think about that you are basically compressing whatever axis that you are giving. So if you have given axis 0, you essentially want to compress axis 0. Okay. Axis 0 in this particular case, okay, is this one along the horizontal line. That means I want to compress this axis to just have one element. Okay. That means I will take a mean of 1 and 7. I will take a mean of 2 and 8. I will take a mean of 3 and 9, and so forth. What is the mean of 1 and 7? You add 1 and 7. This is 8. 7 plus 1 is 8. You divide it by 2. You get what? 4, right? You are getting 4 here. Then you take a mean of 2 and 8. 2 plus 8 is what? 10. 10 divided by 2 is what? 5. You get 5. Let's try this one. 5 plus 11. 5 plus 11 is what? 16. 16 divided by 2 is what? 8. You get an 8 over here. Correct? Now, the dimension of this guy would be this. I can check the shape of this using this. Oops. Oh, I can't do print, right? So I will have to write shape inside, right? So it tells me that the answer is 2 by 3. The answer is what? 2 by 3. Remember what was the shape of this array? If I remind you, it was T1 dot shape. It was 2, 2, 3. I tried taking a mean along axis 0. That means I try actually compressing or basically squeezing the axis 0. Axis 0 got squeezed to 0, and hence the final answer returned was 2, 3, right? Had I taken a mean along axis 1, okay, the final output again would be a 2 by 3, right? Because this one and this one is left. Had I taken a mean along axis equals to 2, this dimension would have actually gotten squeezed. The answer would have been 2 by 2. Let's check it out. Let me say axis is equal to 2. Okay. The answer is actually 2 by 2. And what is the answer? Let's print that also. I'll say T1 dot shape, okay, axis equals to 1 or 2? 2. Yeah. Oops. T1 dot mean. Okay. You see what is it trying to say? It's saying squeeze the axis to. Where is the axis to? So this was my axis 1, or my first axis basically, with axis equals to 0. This was my axis equals to 1 or 2. Think about it. Think along this. It is kind of challenging. It is not as easy as you would think. Let's try to think using some scribbling. Okay, so I'll just go back here. I will say, okay, this is my array. We're using the same array. And what I'll try to do is, I'll try to put these in a single line. Okay, in a single line. Okay, single line would be difficult. Let me just perhaps draw it. I will say 1, 2, 3, 4, 5, and 6. Okay, this is my 1 2D array. This is my second 2D array. 7, 8, 9, 10, 11, 12. Okay, and this is wrapped in another array. And that's what makes it a 3D array. Right? Now, how many elements along my first dimension or axis equals to 0? 2 elements, right? This one, the first one, this one, and this one, right? 2 elements. Now, for number of elements, checking along axis equals to 1, okay, I would have to get inside one of this, right? So in this, my first dimension is this one, right? How many elements are there this side? Again, 2 elements, right? And in my final axis, which I can perhaps use a different color. Okay, let's go with this pinky ponky pink. Axis equals to 2 will be this one. And I'll have what? 3 elements over here. So 3 elements. Now, if I'm trying to say NP dot mean, okay, axis equals to 2, I'm trying to say, hey, squeeze this element, squeeze this dimension. That means you take a mean of 1 and 2 and 3, you take a mean of 4, 5 and 6, you take a mean of 7, 8 and 9, and you take a mean of 10, 11 and 12. Okay? What will be the mean of 1, 2 and 3? 2 plus 1 is 3, 3 plus 3 is 6, 6 by 2 is 3, right? So essentially, after taking mean of this, you would essentially get 3, right? Think about it. When you do an NP dot mean axis equals to 2, all right, you are trying to take, all right, you are trying to actually take a mean along your third dimension or your second axis, which is shown through this pink color. In this one, you will take a mean of 1, 2 and 3. Okay, 1 plus 2 plus 3 upon what? 3, right? This will give you what? 6 upon 3, which is what? 2. Let's check if we got 2 or not. Did we get 2 or not? Yes, we've gotten 2, right? Let's try it for one more. I'll say take mean of 10, 11 and 12, right? Take a mean of this. 10 plus 11 plus 12 upon 3, okay? Upon 3, right? 10 plus 11 is what? 21. 21 plus 12. 21 plus 12 would be what? 33. 33 by 3 would be what? 11. Let's check if we got 11 or not. Yes, our last element is 11. I hope you are able to make sense out of it, and also understand that here I took a mean. I could do np.sum, I can do np.prod, I can do np.median. Whatever operation I want to actually perform on any array on a particular axis, I can do all of that. Now imagine what all it takes to kind of do these operations in native Python. I hope you are able to understand the importance of NumPy and how powerful it is. Okay, so in the last part of this module on NumPy, we talked about 3D arrays, right? We started with 1D array, we went to 2D arrays, and we saw how you can extend this idea to an n-dimensional array, wherein in case of 3D, it's a 3D array, correct? A 3D array is nothing but when you stack multiple 2D arrays on top of each other, right? It becomes a 3D array. Just see the case here. I have one 2D array here, I have another 2D array here, and I'm going to stack it, right? I'm going to stack it simply. And this is where I have created another axis. And remember, the new axis is going to become what? 0. If this axis becomes 0, all right, the old one, this one becomes what? It becomes what? 1. And this one becomes what? 2. Correct? Now it has 3 axes, right? Now, if I'm trying to do a sum across my 0th axis, right? It says axis equals to 0. It's saying that, hey, sum the array across 0th axis. So, essentially that means is that, hey, take all the elements along this axis, which is axis 0, and just sum them up. How many elements do we have along axis 0? We have 2 elements. Remember, one is this element and another is this element. Now, when you sum 1 and 7, what do you get? You get 8. When you sum 2 and 8, what do you get? You get 10. When you sum 3 and 9, what do you get? You get 12, right? However, summing across a different axis would have been different, right? For example, let's say if I say axis equals to 1, this time I want to sum it across axis 1. Remember which one is axis 1? Axis 1 is this one now, all right? This one. And I'm not talking about these two elements. These are along axis 0. Okay, I'm talking about these rows, all right, this dimension particularly. I beg your apologies, of course, like it's very difficult to kind of represent this array in a 3D setting, right? So the two axes essentially would appear to go in the same direction, but these are two different directions. Here I'm talking about when I say I want to sum along axis equals to 1. Remember, the first element is 5. Do a quick guess. What elements would essentially give you a 5? Can 1 plus 4 give you a 5? Can 2 plus 5 give you a 7? Can 3 plus 6 give you what? A 9? Can 7 plus 10 give you a 17? 8 plus 10 gives you a 19, and 9 plus 12 gives you a 21. That means it is saying that, hey, okay, take this element and take this element, just sum it. Take this element and this element, sum it. Take this element and this element, sum it. Now you are essentially summing across the rows, right? So the row axis, the axis along which rows are represented was axis 1. The axis along which columns were represented was what? 2. And the axis along which 2D arrays, all right, were concatenated, that was axis 0. I hope you are able to understand the idea of axes. I hope you are able to understand the idea of ND, 1D array, 2D array, 3D array. See, it's not an easy concept, all right? It takes much more time to kind of get to understand. I would sincerely suggest you that you try a couple of examples here, and even after that, just sync it. Next time when you'll use it, you'll understand it better, all right? I have kind of been known about this axis system for almost 5-6 years, but at the same time, everybody around, I have seen everybody getting somewhat confused about it. So it's more about like practice. And at the same time, it's more about intuition. It's not about remembering. All right. So that's my 2 cents after explaining this. Next thing that we're going to talk about like is a couple of other miscellaneous functions that we can use. All right. Now, let's say this array is a 1D array and it is storing scores of the students. All right. So let's say there's a test and 3 students, let's say, appeared for it. They've scored 85, 92 and 78 out of the test, right? Now I want to check which numbers are greater than 82. Had I been doing it in the native Python, I would have run a for loop. I would say for I in this list, check if it is smaller than 82 or not, or greater than or 82 or not, etc., what is the condition, and just print it, right? Now, what we learned in NumPy is that I can simply just say score 1 greater than 82, all right, and it will give me a true false, right? So for all the places where it shows true, all right, it means that it is actually a number greater than 82, all right. And for all the places where it shows false, that number essentially is smaller than 82, right? Now, what if I have to put multiple conditions into it? For example, let's say I want to check if the number is greater than 80 or less than 90, right? So essentially I want to check if the number is in between 80 and 90, right? How can I do that? I'll say score is smaller than 80, okay? I will put it in the bracket and I'll say score 1 because that's the name of the variable. Okay. I'll explain why I have put it in the bracket and I will write and. But hey, this and is used in the native Python. Here I will not be using this and. Let's actually see what happens when you do this kind of an and. Okay. Let's see. Maybe it works. Okay. Let's say that this should be smaller than 90. Okay. Let's run it. It says an error. It says the truth value of an error with more than one element is ambiguous. All right, because and is not able to understand it. And essentially wants to take two Boolean objects and just wants to compare it, right? So what you do here is you rather put an ampersand. Ampersand is a special character, and okay, this is what essentially is used when you want to work or do an and operation for NumPy array. All right, let's see if it works or not. Yes, now it works. It says, okay, 85 is, okay, did I put a wrong condition? Yes, score 1 should be greater than 80. Okay, let's see the answer now. Is 85 greater than 80 and smaller than 90? Yes. Is 92 greater than 80 and smaller than 90? No. Is 78 greater than 80 and smaller than 90? No. All right, so true, false, false, right? However, at a lot of times, I just don't want an array output of trues and false. All right. I may want to also know the indexes at which the condition is true, right? So simply in that case, what I can do is I can say np dot any, okay? np dot where, okay? When I say np dot where, okay, it essentially, okay, some error. Let me quickly check. Have I put the required number of brackets? No. Let me just put one more bracket. Okay, np dot where. All right. I am trying to ask here, hey, what are those indexes where essentially the number is between 80 and 90? Okay, I could actually do without one more extra bracket. I kind of ended up doing it. So let me just remove it. Yes, it is kind of trailing me that, hey, it is only at index 0 where this condition is met, right? You want to check if this condition, if this np.where functionality is something that you can use actually for checking if this condition is true for multiple cases or not. Shall we make some changes to the condition? Shall I say maybe 93? Okay, 93. In this case, essentially, it should meet for 85 and 92 both, right? So it should give us index 0 and 1. Let's say, yes, it is giving me indexes of both 0 and 1. How cool is it? When you want to just simply get an array of trues and false, you can just get that by, doing the comparison. And if you want to even check which indexes where this condition is meeting, you can just put np.where and you have the answer. All right. Now, more fun part is if you want to check, let's say, if any of these cases meet this condition, or if all of these numbers meet that condition, so you have functions for those as well, right? So in case, if you want to check, let me just write it for you. If you want to check if all the numbers are meeting a condition, okay, then check it by using np.all. And if you want to check, let's say, if all the numbers are, if at least one number, okay, is meeting the condition. Is there even one element which is meeting the condition? Okay, then you actually check np.any. Okay, np.any. Now in this case, I want to check if there's any value, okay, any value that are smaller than 78, right? That are smaller than 78. Is there any value which is smaller than 78? It is not. So what should it say? It should say false. Okay, it should say false. Let me say smaller than equal to 78. It should say what? True. Why true? Because now there is at least one number which is smaller than equal to 78. Now what will happen? Pause off for a minute and figure out that what will happen in case if I say if are all the numbers in this array, okay, actually smaller than equal to 78. Let me say np dot all, okay, and let's check. Of course, it is meant to come as false. Why? Because yes, not all the numbers are smaller than equal to 78. Yes, there is one number which is equal to 78. However, not all the numbers are equal to 78. I don't think this should be very difficult to understand. So I'll quickly jump to another cases as well. We will do one more exercise wherein we'll try to check this condition. It says find indexes where the condition a greater than 2 is true. All right. What it is trying to say is that, hey, I want just the indexes of those cases, right? What do you think where a is greater than 2? It is greater than, is it greater at this index? No. Is it greater than 2 at this index? Yes. And for all the numbers after this, it is greater, right? And what are these indexes? These indexes are essentially 0, 1, 2, 3, 4, and 5. So it should output 2, 3, and 4, 5. Let's see. I'll say np dot what? Where? Any or all? Where? Yes. And I will say, hey, tell me where all, okay, this thing is greater than 2. So I'll say greater than 2. Okay. It says that at indexes 2, 3, 4, 5, the number is greater than 2. I hope this is clear. Now, when you're clear about this, we will now start about learning matrix multiplication. So now, in this specific part, once we've done this, we will talk about matrix multiplication. All right. Matrix multiplication is something that we've seen essentially before also. So here is a matrix. Okay. What do you think? What is the shape of this? Guess the shape of this matrix. It has, okay, 2 rows and 3 columns. So is it 2 by 3? Yes, it is 2 by 3. Okay. Let's see the other matrix. It has 3 rows and 4 columns. So it is what? 3 by 4. Remember, for a matrix multiplication operation to be actually valid, all right, this is 2 by 3, this is 3 by 4. Okay. For any of the matrix multiplication operation to be valid, this and this has to be same. Okay. Okay. The number of columns of the first matrix and the number of rows, okay, of the second matrix, they have to be same. Correct. Now, this is the valid case in our case, okay, and the output here will be a 2 by 4 array. All right. This is essentially how matrix multiplication happens. I'm not going to go into details. You can check out some other YouTube videos or perhaps Google of how to do matrix multiplication, but this is essentially what happens. Now, if you see the output, I'm using np dot function. Earlier, we discussed that you can use @, all right, @ simple also to do a matrix multiplication. The output should be 2 by 4. Is the output 2 by 4? Yes, it has 2 rows and 4 columns. It has 2 rows and 4 columns. So there's no magic over here, right? Matrix multiplication is simple. But where is the magic is something we'll see. So in this case, I'm going to tell you I'm going to give you a simple example. Actually, a real world case of how Numpy matrices can be used. So imagine that you're working for Delivery. Delivery is a supply chain management company, right? I hope you're aware. It's called Delivery. Delivery with Delhi. All right. Started with Delhi. The idea was to kind of deliver things in Delivery, but they have pan-India operations now, perhaps outside also. But yes, essentially it's a logistics company, tries to send your parcel, etc., elsewhere. All right. All of that, right? Now, what happens is that they kind of need to do some kind of forecasting. And for that matter, any e-commerce giant, a warehouse, all of them have to kind of do some sort of a forecasting as well, right? And basis on that, they kind of predict what will be the revenue for the next quarter, next month, next week, etc., etc. All right. Now, in order to do that, they kind of need to know the unit price. That means price of one unit of that product. All right, and there are multiple products. All right, they need to know the unit price of each of the product, and they have to predict how many of those products will be required. How many of those products do you think we will have to deliver, etc., etc. All of that, right? Delivery may have their warehouses. Zepto has their dark stores. Amazon has their warehouses, etc., etc. All of that, right? Now, in this case, I am taking a matrix wherein I am actually putting something in this first matrix. It's a 2 by 3 matrix, and as the description says, it has 2 forecasts and 3 products. All right. That means this matrix is storing 2 different forecasts. All right. So the first forecast model, let's say machine learning model, is forecasting that the product A will be sold 10 units, sorry, 100 units of the product A will be sold. 200 units of product B will be sold, and 150 units of product C will be sold, right? Whereas the second forecast says that 80 products of product type A will be sold, 250 and 120, and so on and so forth. All right. So essentially, this matrix is storing that, okay, what are the two forecasts and what each forecast is forecasting or predicting that how many units of a particular product is sold, right? I have another matrix which is 3 by 3, and what it is storing is, it is storing the per unit prices of those products for the last 3 days. All right. Let's say the prices of those products are changing, right, due to some discount, etc., etc., or it's like, a perishable product, for example, fruits, etc., etc., bananas, apples, and they are perishable, perhaps their prices will also change. So what this matrix is actually giving me is the prices of these products for the last 3 days and their per unit prices, right? Let's say this happens to be my prices of 3 products for the first day. This happens to be my prices for the next day, and this happens to be my prices for the third day, right? When I actually do a matrix multiplication, which is nothing but a dot product, all right, for 2D arrays, right, I gets this kind of an output, right? This kind of an output. Remember, my input matrix one was 2 by 3 in nature. The other one is actually 3 by 3 in nature. The number of columns of the first matrix and the number of rows of the second matrix are same, and hence this matrix multiplication is valid, and the output of this matrix multiplication will be a 2 by 3 array, right? Is it a 2 by 3 array? Yes, it has 2 rows and 3 columns. But what essentially it is giving me? It is essentially giving me the revenue. How? If you want to calculate the revenue essentially will be what? Revenue will be the price of one unit, all right, the number of unit that you forecast, correct? And then there are 2 forecasts. So essentially you get revenue of 2 different forecasts, right? And can you see that there would have been multiple equations or multiple calculations that you would have to do, and matrix multiplication is nothing but just putting that idea together in a simple way wherein it is easy to carry those operations if you have tons of data, right? Essentially, this is what we learned, that hey, I may want to use NumPy for doing my operations quickly, faster, and then in a more simpler way, correct? Now the interesting part is here. I have another matrix which is actually telling me the delivery cost of each product. All right. Say the delivery cost of my first product is 100 rupees. The delivery cost of my second product is 150 rupees, and the delivery cost of my third product is 120 rupees. Now, I may want to add this cost, all right, 100, 150, and 120, all right, to my revenue, all right. And I may want to add 100 rupees, 150 rupees, and 120 rupees to my revenue also. It doesn't matter what is the actual cost of the delivery. It is the cost of the delivery that I am charging to the people. So that actually gets added to the revenue. If you have some basic idea of business, all right, that's how essentially you would calculate the revenue. In general, I would say that, hey, just add revenue and delivery cost. And this is what I'm doing, right? But can you add a 2 by 3? Can you add a 2 by 3 matrix which has essentially what? 3 two rows and three columns to just a matrix which has one row and three columns. No, you need to have something over here, something over here, and something over here, right? That's where broadcasting again is very useful, because NumPy is smart enough to say, understand that, hey, this guy is 2 by 3, this guy is 1 by 3, and I can't add these things, right? Because I don't have enough number of elements in my both the arrays to do an element wise operation, right? But when I have to do this, what I'll do is I'll just simply repeat this thing 2 times. That means it will say that, hey, I will create another matrix 100, 150, 120, adding 100, 150 and 120 2 times, right? Now it has created this matrix and it becomes a 2D matrix of size 2 by 3. Now you can add them. And you don't need to tell NumPy to all of that. Even when you say, hey, just revenue, add revenue and delivery cost, it will just add these together and it will give you the answers, all right, by simply just doing it, all the operations. So NumPy is this smart, right? This is essentially what is called as broadcasting. There are three broader rules for broadcasting, which we will not go into the details, all right, in this course. However, if in case ever you come across the situation where you say, hey, these dimensions are not matching, but somehow the operation is happening, how? You should know that it is broadcasting, right? You don't need to know the rules of the broadcasting. Although if you're curious, you can just say broadcasting in NumPy, 3 rules, etc., etc. You'll be able to find it, right? The next part, we will talk about a couple of just small miscellaneous methods, and we'll just end the NumPy. We have learned a lot. I know NumPy was super cool, but like, trust me, as when you start learning pandas and when you learn matplotlib and Seaborn, the whole horizon will be crazy and you can't just imagine what all you'll be able to build. All right. So let's quickly talk about these miscellaneous methods also, right? We have done, for example, any, where, all these are miscellaneous methods, but we'll talk about one or two more. All right. Let's say you have these two matrices here. Again, these are matrices. Why? Because this is a 2D array. Now you'll be able to see it better when I write it like this. All right. Let me write this also like a 2D array, and you'll be able to understand this part much more better, right? Can you see that these are 2D arrays now? Yes. What is the dimension of these 2D arrays or shape? It is 2 by 2. Both of them are 2 by 2, right? Now, if you want to concatenate them, all right, how do you do? All right, I will say np dot concatenate, okay, concatenate, okay, and I'll say current year, okay, current year and previous year, okay, okay. Colab was doing the job for me, but then I ended up pressing something and it could not. When I say axis equals to 0, it will essentially, okay, np dot concatenate current year, previous year, and axis equals to 0. All right, so I know what is the error. But hey, when I'm trying to use axis equal to 0, what should happen? Should it not actually concatenate these two things along axis 0? Yes, right? But hey, I could actually give multiple arrays and ask np.concatenate to concatenate them. How will np.concatenate understand, what are these all arguments? So I need to put them into the bracket, all right? So that np.concatenate function understands that, hey, this is just one element that you've part, which is essentially a list of some elements, and now it will be able to concatenate them well, all right? I'm actually glad that this error happened. Otherwise, I would have forgotten to tell that you have to put these things within a bracket. So to NumPy to understand that, hey, this is essentially data. You can just add the data. You can put the data, pass the data to NumPy, like, okay, this is array 1, this is array 2, this is array 3, and just you figure out like how many arrays are there, right? You put it in the list and say that, hey, this is the entire data, and you check how many numbers or elements are there, and then you do the operation, right? Yes. Last thing but not the least, we will learn how to transpose the data. Now, what do I mean by transposing? I'll say current year, okay, let me just print it. If I say np dot transpose, okay, np dot transpose, this comes very handy in mathematics, all right? Np dot transpose current year, what it will do, it will essentially change the axis of the array. That means it will turn rows into columns and columns into rows. What do I mean by that? The first column was what? 70,000, 90,000. Look at the first row, 70,000 and 70,000 and 90,000. So what it has done essentially, it has actually converted the first column into the first row. It has converted the second column into the second row, right? And vice versa. That's essentially what transpose means, right? So we've learned the entire NumPy, okay, and I know it must be overwhelming because you've learned a lot of functions. Trust me, you need to understand this intuitively. You need to kind of like do some hands-on work, and you will be able to understand. Do not try to mug up everything. Do not try to learn everything. All of these concepts will become much more crystal clear when you do a couple of questions, or when you start using this to work on the real data. We've not started working with real data yet, but we'll do. All right. And that's where actually the real power of NumPy, or in fact the tools that you learn, all right, in the next module, pandas, matplotlib, seaborn, etc., it may come into the actually life. All right. So see you for the next module on pandas. I hope we remain connected.